So we're going to talk a lot about the normal model or the normal distribution. And this is the bell-shaped curve or one of the bell-shaped curves that you've heard so much about. They're used to model distributions or histograms that are unimodal, meaning one main peak, and roughly symmetric. Okay. Now the key thing to point out is that it's a model, and I find a lot of students kind of forget this. It's a model. So as you can see here, we have a histogram, for rainfall in Dallas, measured in inches, and we could analyze directly this histogram, but that can be kind of tedious, especially since you have to crunch so many numbers, and histograms differ. So it just becomes a pain. But if we use the normal model, which tends to do a really good job of basically describing these such histograms, then we can sort of get great answers that are pretty close to what we want anyway, without necessarily using all the work or having to do all the work. So again, nothing really looks like this perfectly continuous shape here. But it turns out there's a lot of phenomena that when you make histograms of this data, they start to create this like mound symmetric shape, and the normal model can do a great job of modeling that. And we have calculations we can do with the normal model that are quick and accurate, which we're going to look at in a minute. So some notation you want to be familiar with. If you see a capital N, that just means the data is normally distributed. And that first number you see there will be the center. That symbol is called mu. Think of M, the Greek M for mean. And then that sigma is the Greek S for the standard deviation. Okay. So that's just kind of an abbreviation. That just tells you, this distribution of data is normally modeled. That's the center, that's the mean, and that's the standard deviation. And those are really the only two things you need to know to describe the entire population, as it turns out. So those are those are parameters. Now, if when we talk about z-scores, we always basically change our situation so that the center of the data is the mean, which has a z-score of 0, and then we count in terms of standard deviations. So this is just called the standard normal model. And when we do a lot of calculations, we do what's called normalize the data. This is all stuff that will be explained in a minute through an example. Just a little point to make about statistics versus parameters. A statistic is a summary of data. So X with a bar over it is the actual mean of the data you're examining, like a sample you took from a population. Okay, and the S is the actual standard deviation of the data you're examining. So you take a sample of data from a population and you calculate statistics on it. Parameters are actual values of the population. So there is an actual mean height of males in the U.S. Okay, we'll never be able to get all the males to line up and measure their height. But mu would be the true population mean height for males, and sigma would be the true standard deviation. But we always gather a sample and do statistics. Okay, so those symbols represent the statistics we gather on our data. A couple things to notice. One is that area under the normal model corresponds to percentages of the population, okay, that fall into certain ranges of the data. So I just want to note that this is going to add to 100% because that's the entire histogram you're modeling. Okay, the entire histogram is everybody, so that's 100% of the people. And I mean, just in general, you're always going to put your mean right in the center of the distribution. And then, the next tick mark should be, generally speaking, your first standard deviation. And there's your second standard deviation, and there's your third. Okay. And if you go in the other direction, you've gone, -1 standard deviation. Here you've gone -2 standard deviations, 3 standard deviations. Okay, so if I were to just shade this area, that area corresponds to the percentage of the data above 1 standard deviation from the mean. Okay, that area corresponds to the percentage of data values that are 1 standard deviation above the mean or more. So you want to understand that area corresponds to percentage, okay? And again, I emphasize, as long as the shape of the data is unimodal and symmetric, we can use the normal model to help us say something about the distribution. So we'll look at a particular example in the next slide.